Hello mathematicians, thank you for joining me today. Our goal today is going to be that, well, let's let M of A be the set of all mappings on A. And so if I take that set of mappings on the set A and I use composition, then what I'm claiming is that this will form a monoid, namely that the composition will be an operation, it'll be an associative operation, and there will be an identity of this set. We'll do this step by step. The first thing we're going to show is that composition is an operation. So what that means is if I take two things in the set, map them under composition, I'm going to get out a well-defined one thing in the set. So what I'm going to do is just say let's let F and G be two things in the set of mappings on the set A. And I want to show that then F of G is again in the set of mappings on the set A. That is, I'm going to show F of G as a mapping from A to A. So that is, if I pick something in A, it's going to get mapped uniquely to something in A. Alright? So if I think, what does that mean? Well, it means that if I pick an arbitrary element in A, let's say X, then what's going to happen is if I plug it into F of G, I'm still going to end up with something in A. So now how would that happen is, well, let's think about what is F of G of X? Well, the composition of functions means that I'm going to plug X into G, and then I'm going to plug that answer into F. So this is going to be F of G of X. So pictorially what would happen is here's A, and here's X. Now if I think about this, I'm going to plug X into G. G is a mapping from A to itself, so what's going to happen is it's going to send X to some point in A. It might be itself, it might be something else, but it's going to send it to one point in A, and it is going to be exactly one point because G is a well-defined mapping. So I'm not going to get two answers out here, I'm not going to get out 0, I'm going to get exactly one answer. So what I get is that G of X is then an element of A. So what happens is if I plug that into F, F is now going to send that G of X to somewhere back in A. And notice that it's going to go to exactly one spot in A because this was one thing. I plugged it into F, which is a well-defined mapping, so I end up with exactly one output. So what I get now is that, combining that together, I get, well, G of X is well-defined in A. Since F is well-defined, F of G of X is well-defined in A. Hence, F of G of X is well-defined. So F of G of X is indeed a mapping from A to A. Now that we have that composition as an operation, we have to show that it's an associative operation. And so what does associative mean is, well, if I have three things, say F, G, and H are in the set of mappings on A, then what I have to show is that F composed with G composed with H is the same as F composed with G composed with H. So now this is my goal, to show that these two things are the same. So now what I want to do is just think about, well, what does this look like is, well, they're going to be the same if the image of everything in A is the same through these two different mappings. So what I want to show is that for all X, F of G of H of X is F of G of H of X. So now in order to do that, what I'm going to do is just say, well, what would F of G of H of X look like? And so what that's going to look like is, let's calculate this. Well, what this says is to take F of G of H of X. So that means plug X into H and see where it takes it. So if I draw the same picture I did before, here's my set A. X is going to map that to some point, and this is going to be my H of X. Now the next thing I would do is say, well, F of G of H is defined as F of G of H of X. So that means plug H into G. So I'm going to take this answer, plug it into G, and get this answer. And then finally, well, I'm going to take that answer and plug it into F. And I'm now going to get some other answer in A. So this is F of G of H of X. So what I get is, following this through, I would start at X, go to H of X, then go to G of H of X, and then go to F of G of H of X. So now, what I want to do here is, okay, this is just going to be f of g of h of x, so what would it look like if I change the parentheses? So now I'm going to find f of g of h of x, and so what this says is the composition of functions is then, well, this is f of g of h of x. So since I'm taking the composition of these two, that means that I'm going to find g of h of x and then plug that into f. But in order to find g of h of x, what that is just f of g of h of x. So if I follow the same process this time and look at my picture, I'm going to get, well, x is mapped to something under h, so I get h of x. Then I'm going to take that and plug it into g. And then I'm going to take that answer and plug it into f. And so I'm going to get f of g of h of x. So if I do f of g of h instead of f of g of h, then what I get is, well, I'm going to take x, map it under h, map the answer under g, and map that answer under f. Notice that both times I just get f of g of x of h of x. So I map x under h, then under g, and under f. So because I got the same answer both ways, what that means is that, indeed, f of g of h of x is going to be equal to f of g of h of x. So those two functions will be the same, so we will get that composition is associative. Now to finish that, this is a monoid, I have to show that composition has an identity element. So now in order to show that it has an identity element, I have to find the identity element. So that means I really have to kind of guess what it's going to be. And so as I do that, I would think f of, let's say, e should be e of f, which should be equal to f. So the goal is to find a function so that when I compose these, I get out the same thing. So if I think about this, that means that f of e of x is equal to e of f of x is equal to f of x. So as a mapping, what I want is x is going to be some point. I'm going to plug it into f, and I'm going to get an answer. And then when I plug that into e, I just want to stay exactly where I'm at, because that would be the same as f of x. On the other hand, if I look at this, if I do e first, then what I want is, well, eventually I'm going to plug it into f. So the way that I can guarantee that f of e of x was equal to f of x is if this does nothing, then e goes to itself, and then I can get e of x goes back to x, and f of e of x just goes to f of x, and I have what I wanted. So what I have to think about is, what would that mapping look like? Well, I just want it to do nothing, so I'm going to have it send x to x. So I'm going to define the mapping e of x sends x to x, and I want to show that that's an identity. And so really that would follow from, well, this does nothing, so f of e of x is f of x, and e of f of x is f of x, do nothing, we end up with f of x. So we do indeed have an identity mapping on the set A. Now notice that for each of those I did walk through how to do each of them, but I didn't provide you with a formal proof because those are written up on the blog post. So I highly encourage you to visit the blog post and look at how those look when they're formally written. Thank you for joining me today. I hope you found this video helpful. If you did, make sure to like the video and subscribe to the channel.